So basically, we have one last topic remaining to discuss, which are coherent lightwave systems. Okay, so something different from sort of what we've been discussing so far, which are simple IMDD, intensity modulation direct detection systems, right? Which are still the most widely used and simplest to deploy, right? But once sort of very narrow linewidth single frequency lasers were developed, then people realized that we can go for these coherent systems, which can give us some advantages over the IMDD system. Okay, so we'll discuss that in the next couple of classes. Okay, so of course, for the IMDD, we encode information in the optical power, right, or intensity. But you know that from a single frequency laser, we have an electric field which looks like A cosine omega t plus phi, right? So it has an amplitude, it has a well-defined amplitude, frequency, and phase. All these three are very well defined, right? Which means that I can encode information in any of these. And you know that basically with the photodetector, right, it only detects the optical power, right? So for example, if you encode in frequency or phase, just directly detecting on the photodetector won't recover the information, right? So that means we need some other kind of detection, which is what we do in coherent detection. Okay, so what we do is, instead of, so let's say we have our incoming signal, right? So let's say it has some power, average power PS. So this is your bit stream coming in. So I've denoted like pulses here in intensity, but it could be, you'll see that the information is encoded in frequency or phase, in which case this power is actually constant, and then the bits are defined by changes in phase or frequency. So instead of directly detecting it on the photodetector, what we do is first combine it with what is known as a local oscillator. Okay, so basically this is a single frequency laser which has the same carrier frequency as my incoming signal, right? So typically, so you know, so for example, there's a carrier, right? So frequency omega naught coming out of the transmitter, and then we modulate our data onto that, right? So again, the modulation could be, for example, in amplitude or intensity, or we'll see it could be in the frequency itself, or like the phase here. Okay, but this carrier frequency omega naught, right? So we have a laser which is exactly the same as the transmitter. I mean, may not be exactly the same actually. So let's, but somewhere close to the frequency of the this carrier wave of the signal. Okay, so need not be exactly the same, but somewhere close. By close, I mean, let's say within a few gigahertz. Okay, you know, omega naught, the absolute frequency is in hundreds of terahertz, right? So the difference between this local oscillator at my receiver and the carrier of the incoming signal is typically, let's say, a few gigahertz, maximum maybe tens of gigahertz. Okay, so we beat these two on a beam splitter, right? Typically like a 50-50 power splitter. So here I am shown sort of free space, but for fiber optic communication systems, you could have these, of course, in a fiber optic beam splitter. So, right. So you could have a fiber power splitter, a 3 dB splitter, so 50-50, and then in one of the arms you have the photo. Okay, we'll discuss a technique in which you can have photodetectors in both these output arms. But for now, let's assume we just have photodetector in one of the output arms. Okay. Okay, so basically the addition that we've done here is at the receiver we have another laser which is narrow line with single frequency and close to the frequency of the transmitter. Okay, so again, so if this power is proportional to the mod square of the electric fields, right? Here, similarly here. So when we sort of superimpose these two and detect on the photodetector, the photocurrent coming out here will be proportional to the mod square of the total electric field, which will be the sum of the signal and the local oscillator fields, right? So now again we call it coherent because now the fields are adding up. Both these fields have well-defined frequency and phase, so we can actually they add the amplitudes of the fields add up. And so you can see that now the signal will be proportional. So you'll have terms like, so of course you'll have mod ES square, mod ELO square, and then the cross terms, right? And so the cross terms will be proportional to the square root of the power of the signal and the local oscillator, right? Of course, plus some DC terms, which are square of the signal and the square of the local oscillator. So now the main signal, the information that we decode will be from this cross term. Okay. So we'll see that because of this cross term, right? So now the signal that we are getting, the photocurrent that we are getting, depends on the local oscillator. So I have some control at the receiver end, right? Earlier, basically, our photocurrent was just proportional to the power of the incoming signal. But now you can see that we have some control with this local oscillator, and that can actually allow us to boost the performance. Okay, so the advantage is that you can get with this so-called coherent detection, right? So this technique is called coherent detection, where you beat the incoming signal with a local oscillator. Okay, so one is you can improve the receiver sensitivity. Okay, so again, in the direct detection case, the signal was proportional to this mod ES square, the power in the signal. Here, or PS. Here now it's proportional to the square root of PS times PLO, right? And so you can imagine. So if we use a large enough local oscillator power, okay, we can go into what is go into the short noise region. For example, we discussed if you use spin detectors here, we're typically operating in the thermal noise limit. Right? And so that decides the receiver sensitivity. So for example, typically it's around like 2000 photons per bit, right? And we had discussed one technique to improve the sensitivity. For example, having an optical amplifier just before the receiver, right? So-called pre-amplifier. And basically what that did was boost the optical power such that when I detect it onto the photodetector, I'm in the short noise limit, because the short noise scales with the optical power. Right? The thermal noise is constant. And we saw that we could get an enhancement. So we could get the same BER with a lower detected power. Similarly, here, basically we're boosting the signal because of this local oscillator power here. Okay, so which again, basically again here as we increase the local oscillator power, the short noise will scale, and we'll see that basically primarily the short noise will actually just come from the local oscillator short noise. But anyway, so what that allows you to do is to go into the short noise regime, right? And again, if you recall our discussion on receiver sensitivities a few classes ago, in the short noise regime, we can the receiver sensitivity typically improves by maybe 10 to 20 dB from the thermal noise. Okay, so same thing happens here. And second is we can increase the spectral efficiency of our communication system. or IMDD, right? Typically we just have, so bit 1 is high power and then bit 0 is low power, right? And so basically we're just sending 1 bit per symbol, and the spectral efficiency here typically is about like 0.8 bits per second per hertz, right? So which means if I use, so for example, if I use a 50 gigahertz bandwidth, frequency bandwidth, I can do a data rate of 40 gigabit per second. Okay, so that's actually quite poor. Okay. So you know of these other kinds of modulation schemes, right? So for example, so just even starting with the amplitude modulation, right? We could have different levels. Not instead of just 2, we could have m different levels here, right? So that would be what is known as you know, MPAM or MASK, which is amplitude shift keying, with changing the amplitude, right? Or if you are encoding phase, we could have M phase shift keying, where we have m levels of phase, right? You also know about hybrid techniques like QAM, where the amplitude and phase are both modulated together, for let's say amplitude modulation, right? To the base 2 bits per symbol, right? So if m is 4, we are sending 2 bits per symbol, and typically nowadays one even sees like m equal to 64 or 256. Okay, so we are really sending here like a lot of 8 or 16 bits per symbol. So you can see that that really improves the spectral efficiency roughly by a factor of this log 2. Okay. So now, for example, with a 50 gigahertz bandwidth, right? If I had, for example, let's say 16 QAM, right? I could send like 40 into 4, so like 160 gigabit per second, right? Over the same 50 gigahertz, right? And if you want to use any of these kinds of modulation techniques, then basically coherent detection is the only way to go. Of course, right? You can't do direct detection for this. So basically, these are the 2 main reasons why one would go for coherent systems. Okay, so the electric field here of my incoming signal, right, I can write as again an amplitude times carrier frequency and the phase, right? So again, each of these could be a function of time depending on how I'm encoding my bits, right? This could be layers of t, or this could be omega of t or phi of t, right? And then the local oscillator is a pure tone, right? Which means these are constants, right? So this could be a function of time. This could also be a function of time for frequency modulation of this. But for local oscillator, these are constants. So it's a pure tone. Okay, so if I look at this signal here, right, the photocurrent signal, which will be proportional to this mod square of the total electric field. So I'll have, so the first term will be like mod ES square, right? So that will just be the signal power. ELO square, which will just be the local oscillator power. Okay, and then I have a cross term. So that will be ES ELO conjugate plus ES conjugate ELO, right? And using these two expressions, you can see that basically what I'll get is a cosine of the frequency difference between omega naught and omega LO, right? So when I take ES ELO conjugate, I'll get omega naught minus omega LO, right? And the other way around, I'll get this conjugate of that. So when I add those two, I'll get a cosine. So I can write this as okay. So the only time varying, so these two are DC terms, right? They don't depend on time because we're taking mod square of ES of ELO, right? So these two are DC terms. The only time dependent term is this cross term. So this omega IF is the difference in the local oscillator and the carrier frequency from the transmitter. Okay, so typically this is maybe in the few gigahertz range. So let's say 1 to 10 gigahertz, somewhere there. So IF stands for intermediate frequency. So this terminology might be familiar to you from some topics in RF communication or wireless communication also. Right, and this delta phi is basically the phase difference between the signal and the cross. Right, so you can see that this cross term now, of course, so I am getting a signal which is proportional to the amplitude of the signal, also the frequency of the signal and the phase of the signal. Right, so depending on how I'm encoding, from this cross term I can recover my data. And typically my local oscillator power is made much larger than the incoming signal power. Okay, so typically we saw that the incoming signal power here for typical links would be maybe in the microwatt range. Right? So typically local oscillator powers are maybe milliwatt in that range. Okay, and now so depending on this intermediate frequency or the difference between the transmitter and the local oscillator frequency, there are two, so the coherent detection is divided into two main classes. One is homodyne detection, which is where these frequencies are equal. So omega IF is 0, right? So which means the local oscillator is identical to the transmitter. Okay, so in this case, the time varying part of the photocurrent, which is what is which is giving me the information, these are just DC terms, right? So that I can write as, so the responsivity times this, right? So square root of PS times PLO is units of power. So I multiply this by the responsivity to get my photocurrent. Right? Okay. So recall for the IMDD link, right? Basically, my photocurrent was just responsivity times the signal power. Right? So here we are getting this factor of the square root of the local oscillator power along with that and the cosine of the phase. So now you can see that the photocurrents for coherent detection, for homodyne detection, is enhanced by a factor of square root of PLO by PS, or 2 times. Right, that's the enhancement in the photocurrent I get for the same signal power. Okay. So this directly tells you how I can improve my receiver sensitivity. Right, I can get a larger photocurrent for the same received optical power, so which will improve my SNR and right? So that's the enhancement in current. So that means square of this. So 4 times PLO by PS enhancement in the electrical power or electrical, yeah, because electrical power square is I square, right? So my signal is enhanced, the electrical signal is enhanced by this. And typically you see here the local oscillator power is much bigger than the signal power, so this factor can be quite large. Okay, so this factor can be again anywhere between 10 to 100 easily. Okay, so that's homodyne. If the frequency of the local oscillator is the same as the transmitter frequency, and if it is not, it is called heterodyne. Okay, so now in this case, when the frequencies are not, so in this case, when omega f is 0, you can see that actually even here, like the sinusoidal time dependence goes away, right? So now, depending on how you encode data, the time dependence will be here in the power or in the phase here. But this sinusoidal time dependence, that is not present in homodyne detection, right? So in some sense, this is like a, for every bit, this is like a DC photocurrent, right? Within a bit, it's not changing. So for DC photocurrent, we know that the electrical power is I square R. Whereas for heterodyne, the photocurrent that we get is actually an AC current, right? So in some sense, I can write this as a DC current, whereas this will be an AC current because it has the sinusoidal term present. Right. So now again, so this is a sinusoidal current. So we know for an AC current, so the electrical power will be half of I square R, right? So again, it will be proportional to the average of the square of the photocurrent, which will be half of the peak value of the AC current. So okay, so here I'll have a factor of half times the square of this. Okay, so basically the difference between homodyne and heterodyne is, for heterodyne the electrical power I'm getting is half what I'm getting for homodyne, and that's just because in the homodyne case I'm getting sort of a DC current for every bit, whereas in the heterodyne case I'm getting an AC current for every bit. Okay, so the enhancement here you can see is not 4 times but 2 times. Okay, so there's a 3 dB difference in the, for example, the SNR that you will get for homodyne versus heterodyne. So homodyne is better compared to heterodyne by 3 dB. Okay, but that comes at a price, like anything else. So the price you have to pay is that, so here, right, so we've got rid of frequency, and so now we have to just recover the information from the amplitude or the phase here, and so the phase stability, right, so this phi LO has to be really stable. Okay, so we saw that laser has some phase noise, right? So the phase is actually jumping every once in a while, and that actually determines the line width, right? But you can see that if this phi LO is jumping, then I can't recover the phi S, right? So basically, for homodyne detection, you need a really very ultra no phase noise laser, or a very narrow linewidth phase stable laser. Okay. Whereas for the heterodyne detection, you're getting a time varying signal anyway, right? So you're getting an AC signal here. So if you have phase jumps, that doesn't affect you that much, right? Because you're sort of squaring and averaging the current. So I mean, if you have a phase jump here, that doesn't matter. You're averaging over many cycles. Okay, so you can afford to use a laser which has larger phase noise or larger line width with heterodyne. Okay, so heterodyne is easier to implement and more more economical than homodyne, but at a slight loss of performance. Okay, so typically, for example, here homodyne detection also needs what is known as a phase lock loop, an optical phase lock loop. You might have heard about phase lock loops in electrical circuits, but here what you need is an optical phase lock loop. So basically, you have to follow the phase changes of the transmitter at the local oscillator. Okay. So you lock the phase of the local oscillator to the transmitted phase. So you need an optical phase lock loop. So that's quite complicated. Whereas you don't need that for heterodyne. Okay. So now let's see how we can get. So of course we've already seen here that we get an enhancement in the photocurrent, right? So how does that translate to the enhancement in the SNR? Okay, so okay, the SNR we define as sort of the square of the signal current divided by the variance, right? Or this is the variance of the current. So this variance here, again, of course, I can write as a sum of the short noise and thermal noise currents. Okay, again, short noise we call scaled with the photocurrent here. You could include a dark current if you want. Right, so what current will I put here? So again, I erase that. So recall that the total photocurrent that we got was something like the responsivity times vocal oscillator responsivity times signal power, and then the cross term. And this could have right, something like that. So now the biggest term of these three is basically this first term, because the local oscillator power is much bigger than the signal power. So this, oh sorry, there is a square root here. So this is the largest term. Okay, and we know that so the short noise scales with the photocurrent. So each of these components will have its own short noise, but the largest will be this component, the short noise corresponding to this component, because it's proportional to the right. So basically here, this is basically just the local oscillator power which shows up in the short noise, because local oscillator power is much bigger than signal. Okay, so this the short noise corresponding to this term is much bigger than the other two terms. So basically, only the local oscillator short noise shows up. Okay, and this thermal noise, of course, is a constant depending on the load resistance in the receiver much figure of the amplifier and electrical amplifier used and bandwidth. So this is a constant, right? It does not depend on either the signal power or the local oscillator. And then the current here, the signal current here that I will use is basically this part, right? Again, these are DC, they're not giving me any information. So the signal part of the current is just from here, right? So again, if I use heterodyne, so for heterodyne, I can write the SNR. Now in the numerator, I will use again average of the AC square of the AC photocurrent, and in the denominator, I'll have these terms here. So you just write that out. Okay, and so what is this? So this is IAC, right? So the average of IAC square here is again just so half into the square of the amplitude, which is right. So here I can replace 2 times responsivity square PSP. Okay, and if I want to be more specific, I can put the average signal power here, where average signal power is the average of the bit 1 and bit 0 powers. Right, so this is like the P received average that we had. Of course, if you are using like PSK or FSK, then P1 is actually the same as P0. But if you are using ASK, which is just like intensity modulation, then P1 and P0. So anyway, so just to take that into account, we can put an average here. Right, and for homodyne, it will just be twice of this. So for homodyne, I don't have this factor of half because this term goes away here. So for homodyne, basically, SNR again is like twice of heterodyne. This expression times 2. Okay, so now basically the local oscillator power is in our hands, right, at the receiver. So again, typically we choose the local oscillator power. Of course, it's much larger than the received signal power. We also choose the power to be large enough such that this first term becomes large compared to the second term, the thermal noise, right? So the thermal noise is a constant. So we make the local oscillator power large enough such that we can neglect the thermal current, and now we go into the short noise limit, right? So basically we make this PLO large enough that this term is much bigger than this. So that you can see will happen if right, if the local oscillator is larger than this square of the thermal noise current divided by responsivity times bandwidth, then this first term will be much bigger than this term. Okay, and so once we do that, then typically also we can neglect the dark current because that will be much smaller than the average photocurrent received because of the local oscillator power. So basically we end up with the SNR for heterodyne. So you can see we neglect this term, we neglect the dark current, so we're just left with this by this. So the local oscillator power actually cancels out. Okay. So the SNR just scales with the signal power linearly. Okay. So this is basically like the short noise limit. Okay, and the point here is that we can get into the short noise limit even by using a pin photodetector, right? So typically, again, we had discussed that APDs have this like electron or avalanche multiplication, which increases the effective gain or responsivity, right? Which lets me go into the short noise limit. But it, of course, comes with its own problems like excess added noise, etc. But here, even with using a pin photodetector, we can get into the short noise limit via the local oscillator. Right? Similar to, like, for example, when we discussed the optical preamplifier, because of the optical preamplification, we were able to get into short noise limit even with the pin photodetector. So similar. So you know that responsivity, I can write in terms of quantum efficiency and photon energy like that, right? So this I can also write as that, right? And I can also convert this into an effective photon, how the SNR scales with the number of photons per bit. Again, by relating the average signal power to the average number of photons per bit times the photon energy times the bit rate. Right, and then we could put a typical receiver bandwidth of the receiver 3 dB bandwidth of roughly half the bit rate. So if we substitute that in here, you can see that SNR for heterodyne comes out to be just 2 times the quantum efficiency of the detector times the number of photons per bit. Okay, and again for homodyne, it will be twice. So this will be 4 times. Okay, so you can see that. So for example, again, so quantum efficiency is typically between 70 to 90% for a typical in-gas detector that we use, right? So you can see that if you roughly have, for example, 100 photons per bit, or let's say 50 photons per bit, then your SNR is already around 20 dB. Right? Compare it to the thermal noise limit where we needed, like, again, maybe roughly 2000 photons per bit. Okay, and actually this is the same expression that when we were discussing the receivers and discussing the short noise and thermal noise limit, right? So when we were discussing the short noise limit, basically we got the same expression, but with just direct detection, right, it is difficult to go into the short noise limit because we saw that for pin photodetector, typically the thermal noise was larger. And for APDs, you can have sort of higher gain and make the short noise larger, but we saw that that came with again additional added noise. This was multiplied by an excess noise factor, which actually degraded my SNR after some point. So basically here what we can do is get into the short noise limit using a pin photodetector without any of those added complications. Okay, so now let's discuss briefly the different modulation formats that we can use with coherent detection. So the first is just ASK or amplitude shift keying, which is actually just like intensity modulation, right? So basically here the information is encoded in the amplitude. Right, so basically, for example, this could be is some A for bit 1, right? So this will be proportional to the square root of the power in bit 1, and just 0 for bit 0. Okay, so the waveform, the electric field looks like this. So 0 for bit 0, and then cosine omega t with amplitude A for bit 1. Right? So again, if I look at the power, which is proportional to the square of the mod square of the field, then that actually just looks like intensity modulation. Right? So just like on-off key. Okay, and you can use direct detection for this also, because it's just like intensity modulation. But what we'll see is actually if we use coherent detection, right, even for intensity modulation or amplitude shift keying, we can get an improvement over direct detection. Okay, so then next is phase shift keying. And again, so this is just simple 1 bit per symbol, but you could also have multiple levels, like again, the M levels you were talking about. So that would be MASK. So phase shift keying is now we encode in the phase, right? So I can write this as, so amplitude is now constant. And information is in the phase. So now this phase is, let's say, 0 for bit 0 and pi for bit 1. Right, so you can represent this again like in a constellation diagram or something like this. Right? So this bit, this phase 0 and this phase pi. So this is 0 and 1. And again, so this for m equal to 2, you could have more m levels which will lie on the circle. So F4 will be 2 points here. So that will be 0, 0, 0, 1, 1, 0, 1, 1. Okay, so so that's phase shift keying. So the amplitude, so if I look at the power, that's actually constant, right? So you can, for this of course, but with direct detection I cannot recover the information because the intensity is constant. And so phase shift keying, typically, if you want to implement this pure form of the phase shift keying, then basically since the information is encoded in the bit, right? So in the phase, so let's say this is bit 0 and then bit 1. So the phase is pi out of phase with this. So of course, you're looking at the absolute phase of the bit, right? So if I have a very long bit stream, my phase has to be stable over that entire bit stream, right? So if I'm sending whatever 10 billion bits, then my phase has to be stable for that entire 10 billion bits, right? So for example, if I have 10 gigabit per second, then I take 1 second to send those 10 billion bits. My phase has to be stable for 1 second if I want to measure the phase, the absolute phase for each bit, right? Because if the phase jumps somewhere in the middle, then let's say if it jumps here, then I don't know if it was 0 and then jumped to pi, or was it pi already. So you need an absolute, you need like a very good phase stable laser to implement this pure form of PSK, okay, with absolutely very low phase noise, which can be done but is typically very, very expensive. If you take the typical semiconductor lasers, what is easier to implement is what is known as differential phase shift keying, or DPSK. So there what we do is encode the information in the difference of the phase of consecutive bits. Okay, so now we look at phi k minus phi k minus 1. So we look at the phase of the kth bit and the previous bit, k minus 1th bit, and the difference between the two. So if this was 0, so if both of these had the same phase, then we say we decode the kth bit as 0. But if they were out of phase, so if phi k and phi k minus 1 was plus minus pi, then we decode the kth bit as 1. Okay, so now you can see how this. So the requirement now that I need is phase stability over just 2 bits, right? Because I'm just measuring the difference between consecutive bits. So, so roughly, if my phase is stable over at least 2 bits, then I can measure the right. So, for example, let's say, so you measure these 2 bits, and then there was a phase jump. Okay, so there was a phase jump, and now the next 2 bits. So after the phase jump, let's say at the transmitter I had sent 0, but now at the receiver I have pi, right? But now because this phase has jumped, 0 became pi and pi will become 0, right? So if at the transmitter I send 0 and pi, at the receiver I get pi and 0, but I still decode the bit correctly, right? Because the information is in the change in the phase from bit to bit, right? So as long as the similarly, if you are 0 0, you receive pi pi, again your recovered bit is correct, right? So basically, what you need is the phase to be at least stable over the time scale of 2 bits. So again, if you have 10 gigabit per second, now you're talking about a phase coherence over a time scale of 2 bits, so that's 200 picosecond. So that is a much more relaxed requirement from the laser. So you can use like conventional semiconductor lasers and implement this DPSK very easily. Okay, so typically in the field, this is what is typically implemented as compared to pure form machines. Although in some some cases you do see PSK, but you require then very extremely good lasers which are quite expensive. Okay, so and then finally you could also encode information in the frequency. So that's FSK, frequency shift key. Okay, so there basically my electric field again has some constant amplitude. Now my frequency varies with time with the bit. So this omega t, so for example, is a slightly higher frequency for bit 1 and slightly lower frequency for bit 0. So I shift my carrier frequency slightly for the 2 bits. So it looks like this is of course exaggerated. Okay, so if this is bit 0, then this is 1. So typically, of course, delta omega is much smaller than omega naught, so you can't visually see it like that. So there's this modulation index defined, which is the frequency modulation index beta, which is defined as the frequency shift divided by the bit rate. Right? So there's a bit duration here, TB, which is 1 over the bit rate. And there's a frequency shift which I'm doing for each bit. So the relation between the two. Okay. So if you look at the total, if you take again like sort of the Fourier transform of this bit stream and look at the total bandwidth of the signal, so that's typically twice of the bit rate plus twice of this frequency shift. Right? So delta omega here is again 2 pi times delta f. Okay, so the bandwidth is determined by the bit rate and this frequency shift. Okay, so now if this modulation index is small, right, which means the frequency shift for each bit is much smaller than the bit rate. So typically, so let's say bit rate is 10 gigabit per second, but the frequency shift is only 1 gigahertz. So this will be 0.1, right? So for bit 0, my frequency is 1 gigahertz lower than omega naught, and for bit 1, frequency is 1 gigahertz higher than omega naught. Okay, so beta will be 0.1 then. So you can see that the bit rate, so the bandwidth will be determined by the bit rate. Whereas if my frequency shift is much larger, so let's say for 10 gigabit per second, I shift my frequency by 100 gigahertz. Right, so my 100 here, the carrier frequency is 100 gigahertz lower, here it's 100 gigahertz higher. So then my bandwidth will be determined by the frequency shift. Okay, so this is typically the first case where the modulation index is small. That's known as narrowband FSK for obvious reasons. It's narrowband. The bit rate is determining my bandwidth, which is what it does for other kinds of modulation schemes also, right? Like even for simple intensity modulation, typically the bandwidth occupied by the signal is proportional to the bit rate. In the other case, it's known as wideband FSK, where now my modulation, the frequency modulation is determining the bandwidth. Okay, so broadly, these are the 3 kinds of modulation schemes I can have, and of course there are some other kind of schemes which are some variations or combinations of these, right? So QAM is a combination of these two. And there are slight variations on some of these, but so fundamentally these are the sort of three schemes you can have, and now you can build more complicated schemes with some modifications or combinations of these. Okay, so okay, so let's see how we can for these kinds of signals, right? Using coherent detection, how we can demodulate these kinds of signals. And then we'll compare sort of the performance that we can get in these different types of modulation schemes using coherent detection. Okay, so typically the demodulation schemes are classified into two broad classes. One is synchronous demodulation, the other is asynchronous. Okay, so in synchronous demodulation, we directly get the baseband signal where our information is encoded. Whereas in asynchronous demodulation, we first get an intermediate frequency signal, just like sort of like with homodyne and heterodyne. Right? With homodyne, we directly get like a baseband signal. We remove the frequency because the local oscillator is exactly the same frequency as transmitter. Whereas in heterodyne, we first get an intermediate frequency signal. Right? So you might think then, of course, homodyne is synchronous and then heterodyne is asynchronous. But so by definition, homodyne has to be synchronous because directly we get the baseband signal. But we'll see that for heterodyne, we could also have like synchronous heterodyne and asynchronous heterodyne. We'll get to that in a minute. But so here basically you first get an intermediate frequency signal. So again, this is let's say the few gigahertz range, and then sort of filter it to get the baseband signal with information. Okay, and so just like the homodyne heterodyne case, this is sort of easier to implement, the asynchronous case, easier and cheaper to implement. This is, it has more requirements on the performance of the components that you need, synchronous, but can give you slightly better performance. So homodyne, so homodyne is by definition synchronous, whereas heterodyne can be synchronous or asynchronous. Okay. So homodyne synchronous, homodyne means synchronous already, and homodyne, this is just what we sort of discussed already. right? So directly we just have our signal, local oscillator, beat the two and detect on photodiode. So the frequencies here are the same. Okay, so we directly just get a baseband signal, and the photocurrent coming here is proportional to sort of cosine of the phase difference. Okay, so for homodyne, basically all we need is the local oscillator to be phase locked and frequency locked to my transmitter. Once I have that, then I just beat and detect. I don't need to do anything extra. Okay, but as you saw, this is a challenge to have the local oscillator to be exactly frequency and phase locked to my transmitter. So now let's look at these two cases for the heterodyne. So first, if you look at heterodyne synchronous. So here what I do, again, I have my incoming signal which I beat with the local oscillator. But now of course, so this omega naught and omega LO is not equal. Okay, I detect it on my photodiode, get a photocurrent, right? So now this will have like cosine of omega naught minus omega LO times t. So it's an AC signal here. Okay, so what do? I first have a band pass filter. To filter out that intermediate frequency. So this is centered around omega IF. Okay, so for example, I can remove the DC components. So here I'm left with so I remove the DC components proportional to the local oscillator and the signal powers, and I'm just left with the cross term. So this will be something like this. Okay. Okay, and then so let's say I'm doing phase shift keying and I want to recover the information in the phase here, right? So what you do is do a carrier recovery. Okay, so this is some electrical phase lock loop circuit, PLL, electrical PLL circuit. So you might have heard of some circuits like Costas loop or squaring loop or something. So some electrical PLL circuit which does carrier recovery, basically it recovers this frequency omega IF and also locks the phase okay, so we multiply these two. So here sort of you're getting something which is like cosine omega IF times t. Okay, so now you multiply these two. So using the product of the cosine formulas, you'll have a term which is, so one term will be the difference of these, which will be cosine of this phase difference. The other term will be the sum of these two, which will be at a frequency twice of omega IF. Right? So after this, I put a low pass filter to remove the, so basically this low pass filter, so 2 omega IF is somewhere here, right? And basically my baseband signal is what I want. So what I'll get here is just cosine of the phase difference. Okay, now so now you can here, so for example, if you have PSK where phi s is varying between 0 and pi, so now your current here will be so cosine 0 or cosine, so it will be 1 or minus 1 depending on the bit you set. Okay. So yeah, so here basically, so this is T, then here the current is proportional to the bit stream. Okay, so now so you can see that it's quite complicated, right? So synchronous system, you need these electrical filters, and you also need this PLL circuit, electrical PLL circuit. So it's a bit complicated. The receiver is a bit complicated, but it gives, we will see that it gives better performance than asynchronous. Okay, so if the amplitude of the current here is IP, that is, we call this responsivity times square root of the linear local oscillator powers. Okay, so if you include the noise, the receiver noise here again, like short noise, thermal noise, this current will have a noise component, right? So the IF of T here, so if I write this as some, so this I write as IP of cosine omega IF T plus some delta phi. Okay, so here, so I can use the cosine rule here, so I can write it as IP cosine omega IF T cosine delta phi. Right, plus IP sine omega IF T sine of delta. Okay. So I just use cosine of A plus B rule here. Okay, so you can see, so this is like these two are quadrature terms. If that term is familiar to you. So this part of the current goes as cosine omega t, whereas this part of the current goes as sine omega t. Okay, so these are what are known as the in phase and quadrature phase parts of the current, I and Q parts of the current. So hopefully that is familiar to you from your digital communications or basic communications course, right? So, so in addition to this signal currents, the in phase and quadrature phase signal currents, basically you have noise currents added from the photodetector to each of these two components. Okay, so the total current with noise I can write as sort of, so this is the in phase component which has its noise, in phase noise current. Okay, which goes as cosine of omega t, and then the other part is the quadrature, which is sine, and this is a quadrature noise current Q, which goes as sine of. Okay, so again, so this IP is basically proportional to, okay, and this is the noise current. In phase okay, so each of these could be composed of again like short noise and thermal noise. But again, if our local oscillator power is typically large enough, then they will primarily be determined by short noise. There's a question: will it be minus? So it doesn't matter. I guess yeah, maybe there's a minus here. I don't know. Doesn't matter. So you can include the minus with like here with the carrier if you want, or right. So this will be like cosine omega t and cosine omega t plus pi by 2. But yeah, that minus sign doesn't really matter. Okay, so now what we are doing here, right? So now we are doing this carrier recovery and then multiplying by cosine omega t. So if I write the current as something times cosine omega t plus something times sine omega t, now I multiply that thing by cosine omega t and do a low pass filter, right? So you can see that only the cosine in phase term will pass through the low pass filter, right? Because cosine, I'll get a cosine square which has a DC term, right? So that will pass through the low pass filter. But the cosine multiplied by sine will give me a sine 2 omega I of t, which will be cut out by the low pass filter. Okay, so this term is cut out by the low pass filter. Right. So after the low pass filter, I only have my in phase component remaining. Right. So these noise currents have their own are basically like noise currents that we discussed already. Average value is 0. Average of square includes short noise and thermal noise. Okay. But here, basically, after the low pass filter, if I call this my baseband current, this is now I'm just left with the in phase component. Okay. So finally, what I detect is just the in phase component and its noise. So the SNR and then the BER performance will be determined just by the in phase. Okay. So that's the synchronous detection. Okay. So we recover. So first we band pass filter the intermediate frequency, then we recover the carrier, multiply the filtered current with that carrier, and then low pass filter to get the in phase component and remove the quadrature. So let's now look at asynchronous quickly. Okay, so in that case, basically the receiver is simpler. So again, I wait my incoming signal with the local oscillator, detect from the photodiode, bandpass filter the intermediate frequency, and then after this I have a much simpler circuit. I don't need a PLL or anything. Okay, so what I do, so again I have this IF of t, which is something like okay, and then I have an envelope detector. And then a low pass filter. Okay, so instead of this carrier recovery and the electrical phase lock loop, I just use a simple envelope detector. Right, envelope detector is so if you have some AC signal whose amplitude is varying, the envelope detector just detects the envelope or the how the amplitude is varying. Right, so it could be a simple RC circuit, for example, right, whose time constant is much slower than the carrier frequency. It just follows the. So the envelope detector is very easy capable. Okay, so what does the envelope detector do? So again, if I write this as some in phase component plus quadrature okay, so here it just gives me sort of the square of, right, so it just gives me the envelope which is the square of these amplitudes. Okay, so in this case, okay, the final the baseband current that I get okay, so again I can write this current after the bandpass filter as in phase with noise plus the quadrature phase current with its own noise. Okay, and then basically the envelope detector just takes the time independent part, right? So it takes so just get okay. Square root of a square plus b square. So you can see for the asynchronous case, the receiver is much simpler, but my quadrature phase noise also the noise in the quadrature phase component, the Q component also comes into my final baseband. Right? In the synchronous case, only the in phase component pass through the low pass filter, but here there will be also the quadrature part. Okay, so because both I and Q components of the noise end up in the baseband signal, the SNR is lower. Compared to synchronous. Okay, so if you talk about the receiver sensitivity in terms of how much power, signal power you need here to get a particular VER, then the sensitivity is degraded, which means you need slightly higher power if you use asynchronous detection. But that degradation is typically again within 3 dB. So the degradation from synchronous to asynchronous is between 1 and 3 dB typically, depending on the exact components used. So that is not too much of a penalty to pay for using such a simple circuit instead of the complicated electrical phase law. Okay, so typically in most cases we use asynchronous. On only certain rare cases where your performance is really you can't compromise on your performance at all, then you go for synchronous. Okay. So it's like a trade-off between homodyne and heterodyne. Heterodyne is much simpler to implement. You don't need this optical phase lock loop to lock the frequency and phase of the local oscillator to your transmitter. But there's a 3 dB penalty in terms of SNR. Similarly, for asynchronous, the receiver circuit is much simpler. You can just use the envelope detector, but the SNR that you get is slightly lower than what you get with synchronous. Typically, again, slightly lower by maybe 1 to 3 dB in that range. Okay, so just one final point here. So you can use these schemes like for the traditional ASK, PSK, FSK kind of modulation schemes. For this modified PSK, the differential phase shift keying, right, where we are looking at the difference in the phase of two consecutive bits. There, basically, what we do. Again, so here you have your photodiode, photocurrent here, bandpass filter at the intermediate frequency. Okay, and then basically what you can do is just, so here you have your current again, which is like an AC signal at the intermediate frequency, right? And now basically I want, so this is an asynchronous receiver for DPSK. Differential phase shifting. So there basically you want to see this phase between consecutive bits. So what you do is you do a 1-bit delay here. Okay, and then multiply the delayed signal by 1 bit with the current bit, right? So here basically you will have something like cosine of omega IFT. Again, so if I write this delta phi as so the kth bit minus the local oscillator, right? I do a 1-bit delay, so here now I have the k minus 1s phase of the k minus 1s bit. So again, when I multiply these two, so the baseband signal will be the difference of these two. So that will, you can see omega t will cancel out, and I'll have phi k minus 1. So if I do a low pass filter after this, here what I'll get is cosine of phi k minus 1, which is what my bit. From the value of this, I can decode my k bit. Right. So if this is cosine of 0 equal to 1, then I can say, okay, my k bit is 0. If this cosine of pi or minus 1, then I'll say my k bit is 1. So for the DPSK, you need this 1-bit delay instead of the envelope detector. Just a detail. Okay, so we'll stop here. And so in the last remaining class on Thursday, we'll just sort of compare the performance of these different modulation formats, ASK, PSK, FSK. So what are the fundamental limits in terms of receiver sensitivity, and which scheme can in principle perform better. And look at some, again, effect of some other kinds of noises on the performance, like relative intensity noise in, for example, my local oscillator. My local oscillator is also not perfect, right? So relative intensity noise, maybe phase noise in my local oscillator, how these things will affect the performance.